On June 8, 2021, roughly 85% of Fastly's global content delivery network went offline. BBC News, Reddit, Twitch, The Guardian, gone. Simultaneously, for just under an hour. The kind of outage that, when you see the scope of it, makes you assume something catastrophic happened. The actual cause was a single customer changing a single setting. That setting triggered a latent software bug that had been sitting dormant in Fastly's infrastructure for months. The bug caused a configuration to be provisioned across their global network, a configuration that looked valid, that passed internal checks, that their systems accepted and distributed without error. And then 85% of the network crashed. The provisioning succeeded. Every system that processed it said so. The configuration was wrong. Nothing said that. This is the incident that explains something fundamental about how cloud systems fail, and why a deployment reporting success is one of the least informative things your infrastructure can tell you. Because it provisioned and it works are not the same statement. They never were. And the gap between them is where some of the most expensive, most disorienting, and most preventable incidents in cloud engineering live. When you apply a Terraform plan, the output tells you how many resources were added, changed, and destroyed. When you deploy a CloudFormation stack, it tells you create complete. When you call the AWS API to launch an EC2 instance, it returns a 200 with an instance ID. When you push a Kubernetes deployment, kubepelt tells you the deployment was created. Every one of these confirmations means the same thing: the request was accepted. The system has begun doing something in response to it. What that something is, whether it completed correctly, and whether the resulting state is what you asked for, none of that is in the confirmation. Think about how this works when you order something online. The order confirmation arrives within seconds. The item might ship tomorrow. It might arrive damaged. It might not arrive at all. The confirmation told you your request was received. It told you nothing about what you'll actually have in 3 days. You understand this implicitly with online orders. So you check tracking, you wait for delivery, you inspect the package when it arrives. Now think about how most deployment pipelines treat a 200 from the Cloud API. They move on, they mark the step complete, they proceed to the next stage. Because the confirmation arrived, and somewhere in the culture of software deployment, a confirmation became synonymous with completion. It isn't, it never was. The distance between request accepted and resource exists, is correctly configured, and is ready to serve traffic, is where provisioning happens. And provisioning can fail at every point along that distance without sending you a notification. Partial provisioning, a system that is neither fully built nor clearly broken, is harder to deal with than either a clean failure or a clean success, and it's far more common than engineers expect. Here's what it looks like in a CloudFormation deployment. You have a stack of 40 resources. The stack starts provisioning. Resources 1 through 26 complete successfully. Resource 27, a security group rule, fails because of a dependency that wasn't fully ready. CloudFormation begins rolling back. But rollback is itself a provisioning operation, and rollback can also fail. 4 resources from the original deployment resist deletion because other systems have already taken dependencies on them. The stack ends in rollback fad. You now have a system that is neither the old state nor the new state. It's a third state that was never designed, never tested, and has no runbook. Here's what it looks like in a Kubernetes deployment. You push a new version of your application. The deployment controller begins replacing old pods with new ones. The new pods start, pass their readiness probes, and receive traffic. 40% of the way through the rollout, a pod fails to start. A misconfigured environment variable, a missing secret, a dependency that isn't available in the new configuration. Kubernetes stops the rollout. Your cluster is now running a mix of old and new pods simultaneously, splitting traffic between 2 different versions of your application, neither of which was designed to coexist with the other. Here's what it looks like in a Terraform apply that times out. The apply runs for 20 minutes and then the terminal session is lost, a network issue, a laptop lid closed, a CI runner that hit its job time limit. The apply may have completed, it may have stopped part way. The Terraform state file may or may not reflect what actually exists. You run Terraform plan and it shows changes, but are those changes from the incomplete apply or from drift that already existed? You don't know, and applying again might create duplicates or skip things that were partially created, or fail because resources already exist under different names. In all three cases, the system is half-built. It looks like it's running. Metrics are green. Some services are responding. The dashboard shows no obvious errors. The damage is in the configuration, in the relationships between resources, in the state that wasn't reached, and it will stay invisible until traffic hits the path that relies on what wasn't built. The reason partial provisioning states are so consistently dangerous is that they are designed to look healthy. Standard monitoring checks whether things are up. Is the service responding? Are the instances running? Is the health check passing? These are the right questions for operational failures. A server that crashed, a process that exited, a disk that filled up. They are the wrong questions for provisioning failures, because provisioning failures don't take things down. They build the wrong things, or leave things partially built, or build things in the wrong configuration. And wrong configuration, running on healthy infrastructure, produces healthy infrastructure metrics. The Fastly incident is the clearest illustration of this. Their infrastructure was running, every node was up, the CDN was processing configuration updates. All the metrics that measure whether the system is operational were showing normal values because the system was operational. It was operational in the wrong configuration. The monitors watched for failure. The failure was a successful provisioning of a broken state. This is why provisioning failures are disproportionately likely to cause user-visible impact before any internal alert fires. The internal monitoring sees healthy infrastructure. The user sees a broken product. The gap between what the system reports about itself and what the user experiences is filled exactly by the provisioning state that nobody verified. Catching this requires a different class of monitoring, one that checks not just whether components are running, but whether the system is in the state you intended to provision. Configuration verification. Deployment validation. Post-provision smoke tests that check actual behavior, not just process health. These are not standard, they require deliberate investment. And they are almost always added after the first incident that makes their absence expensive. Every provisioning failure in this category, partial state, silent misconfiguration, configuration that passes validation and breaks production, has the same root: the assumption that provisioning is a transaction. In database terms, a transaction is atomic. It either completes fully and commits, or it fails fully and rolls back. You never end up with half a transaction in your database. The guarantee is absolute. Cloud provisioning is not a transaction. It is a distributed, asynchronous, eventually consistent process that involves dozens of internal systems, each of which can fail independently, each of which has its own retry logic, its own timeout, its own definition of success. When you provision a VPC, AWS creates networking components across multiple internal systems that don't share a transaction boundary. When you deploy a Kubernetes workload, the scheduler, the kubelet, the container runtime, and the CNI plugin all participate independently. When Fastly distributed that configuration, it propagated across nodes in sequence, not atomically. None of these systems can give you a transactional guarantee because they are physically distributed systems, and physical distribution makes atomicity impossible at scale. What they give you instead is a confirmation that the request was accepted and the process was started. What happens next is asynchronous, distributed, and observable only if you're watching the right things. The engineers who understand this don't trust deployment confirmations, they verify outcomes. They write post-deployment checks that confirm the actual state of the system matches the intended state. They treat a successful apply as a hypothesis to be tested, not a conclusion to be celebrated. One customer, one setting, one latent bug. 85% of a global CDN offline for an hour. The provisioning succeeded. That's what made it dangerous. If it had failed, the error would have been caught before the configuration reached the network. Instead, it succeeded, silently, completely, correctly, into a broken state that no system flagged, because no system was checking whether success meant what everyone assumed it meant. Cloud provisioning is not a command that executes and confirms. It is a request into a distributed system with its own timeline, its own failure modes, and its own definition of done, which is frequently different from yours. A 200 means the conversation started. It doesn't mean it finished. It doesn't mean it finished correctly. And it definitely doesn't mean the system is now in the state you intended. Knowing that difference and building the verification that closes the gap is one of the most consequential things you can do for the reliability of any system you're responsible for.